Welcome to today's Explainer. We've got a fantastic topic lined up. Our goal right now is pretty simple, but it's incredibly exciting. We are going to strip away all those Hollywood sci-fi tropes, bypass the overwhelming buzzwords, and figure out what artificial intelligence actually is. We're going straight to the source text to trace the whole fascinating journey of AI, from its early philosophical roots right down to the very real structural mechanics that are powering our world today. So get ready, because this is a deep dive that'll completely reshape how you view the technology sitting right there in your pocket.
So let's jump right in and look at where this whole discourse actually began. You really can't talk about artificial intelligence without talking about the father of computer science himself, Alan Turing. I mean, decades before we had smartphones or even the internet, Turing published this landmark paper called Computing Machinery and Intelligence. And in it, he posed the ultimate question: can machines think? It's a profound, honestly kind of jarring question to ask back when computers took up entire rooms and ran on vacuum tubes, but it perfectly set the stage for literally everything that followed.
To answer that monumental question, he came up with what we now famously call the Turing test. Basically, it involves a human interrogator trying to figure out whether the written answers they're getting are coming from an actual human or a machine. Now, what's really interesting here is that even though this test has faced considerable scrutiny over the years, it remains an absolutely essential piece of AI history. It's a continuous, ongoing philosophical thought experiment, deeply rooted in principles of linguistics, and it's essentially what sparked the entire field.
But as the field matured, the purely philosophical kind of gave way to the practical. Take this incredibly insightful quote from John McCarthy at Stanford University back in 1955. He defined artificial intelligence quite a bit differently. He called it the science and engineering of making intelligent machines. So the crucial takeaway is that McCarthy shifted the whole focus from a philosophical question, can they think, to a hard science engineering problem. He also pointed out that while AI can help us understand human intelligence, we don't actually have to limit our programming methods to what is biologically observable in humans. It was a massive leap forward.
Section 1. The 4 aims of AI.
That tension between imitating humans and simply engineering intelligent solutions brings us right to how modern experts categorize the goals of AI today. In Stuart Russell and Peter Norvik's highly influential textbook, Artificial Intelligence: A Modern Approach, they distinguish computer systems based on reasoning and thinking versus acting. It's a brilliant matrix. We have the human approach, systems designed to either think exactly like humans or act exactly like humans. And in contrast, we have the ideal approach, which focuses entirely on rationality, meaning building systems that think rationally or act rationally regardless of how a human would actually do it. It beautifully frames the different paths AI researchers take.
Section 2. The mechanics of AI.
Okay, so we've talked history and philosophy, but let's actually get under the hood here. What exactly is artificial intelligence today? In its simplest, most technical form, AI is a discipline that combines computer science with substantial data sets to enable complex problem solving. And it includes those deeply integrated subfields you've probably heard of, like machine learning and deep learning. These fields consist of specific AI algorithms aimed at developing what we call expert systems. The ultimate goal here? To make highly accurate predictions or classifications based on the input data. At its core, modern AI is literally just about using sophisticated algorithms to turn massive amounts of data into expert predictions.
Section 3. Navigating the hype cycle.
Of course, whenever you combine massive data sets with cutting-edge computer science, you are bound to generate some serious excitement. As expected with any developing tech, AI is currently surrounded by a great deal of hype. According to Gartner's famous hype cycle, things like self-driving vehicles and personal assistants are following a very normal evolution of innovation. It's essentially a roller coaster. Step 1, massive overenthusiasm. Step 2, a steep drop into disillusionment when the tech doesn't instantly solve every single problem we have. And finally, Step 3, an ultimate realistic grasp of the innovation's true importance and position in the market.
To ground this theory in our present day, let's look at a stark reality check from Lex Fridman's 2019 MIT lecture. He noted that we are currently sitting right at the very top of inflated expectations, and we are rapidly nearing that trough of disillusionment. And it is incredibly important to keep this in mind when evaluating what AI can and cannot do right now. We absolutely have to separate the hype from the actual utility.
Section 4. Real-world application, AI in finance.
So if we strip away all that over-enthusiasm, what are the concrete, current market applications? Let's take a look at a specific, highly regulated sector that is heavily relying on these expert systems today, the financial services sector. This breaks down AI hard at work in the real world. Over in investment services, we see AI being used for algorithmic trading and robo-advisory. In lending, it's driving retail and commercial lending scores, even detecting the possibility of default. Down in audit and compliance, it is powering massive fraud detection systems. And in customer service, it's used for KYC, know your customer, and predicting customer churn. This isn't science fiction at all. This is AI processing data and making classifications today.
Section 5. Weak AI versus strong AI.
Seeing those specific financial applications perfectly sets up our next major concept. We really need to clearly demystify what we have today in the real world versus the sci-fi future we constantly imagine. The crucial point is how we categorize an AI's capability. First, we have weak AI, also known as narrow AI, or artificial narrow intelligence. These are systems strictly trained for particular tasks. In stark contrast, we have strong AI, which encompasses artificial general intelligence and artificial superintelligence. These represent machines that possess general, human-level, or even superhuman intellect.
Let's break down weak AI first, mostly because the name is honestly a bit misleading. Weak AI is anything but feeble. It actually powers the vast majority of the AI that surrounds us every single day. Because it's heavily trained and honed to do particular tasks incredibly well, it allows for some very sophisticated applications. Think about Apple's Siri, Amazon's Alexa, IBM Watson, and even those driverless cars. They are highly capable, but their intelligence is entirely narrow and task-specific.
Then we cross over into the realm of strong AI, starting with AGI, or Artificial General Intelligence. This is a hypothetical kind of AI where a machine possesses actual human-level intellect, self-aware consciousness, and the innate ability to solve problems, dynamically learn, and plan for the future. I really want to stress the word hypothetical here. While it's exactly what we see in the movies, AGI is totally theoretical at this point and has absolutely no practical applications in the market right now.
And taking it one step further into the theoretical, we get ASI, or Artificial Superintelligence. This is a form of strong AI that wouldn't just match us, it would completely transcend the intelligence and capabilities of the human brain. Again, this is entirely hypothetical, but that absolutely does not stop AI researchers from actively studying its potential development. It's essentially the ultimate ceiling of what an artificial system could theoretically become.
Because we don't have ASI in the real world yet, we have to look to pop culture to really visualize it. Perhaps the finest instance of artificial superintelligence comes straight from science fiction. Think of HAL from the movie 2001: A Space Odyssey. A superhuman, completely self-aware, and ultimately rogue computer aide. That is our cultural touchstone for what ASI could be.
Which brings us to the ultimate question that connects everything we've talked about today. We've seen the philosophical origins of Turing's test, the hard engineering of modern expert systems, that wild hype cycle, and the very real gap between narrow AI and artificial superintelligence. So I leave you with this to chew on. Will our narrow, data-driven expert systems ever truly evolve past Turing's test into a self-aware HAL? Or, as the hype eventually fades, are we destined to just stay in that trough of disillusionment, relying forever on highly efficient but ultimately narrow algorithms?
We're tackling a really fascinating challenge. We are going to break down some of the most intimidating buzzwords in tech right now. If you've been hearing terms like artificial intelligence, machine learning, deep learning, and robotic process automation thrown around, and you've kind of wondered how they actually connect to create a modern digital workforce, well, you're in exactly the right place. We're going to strip away the jargon, look at the structured insights, and give you a crystal clear understanding of what these concepts really mean and how they actually work together in the real world. Okay, let's dive right into our roadmap for today. First, AI and its subfields. Second, machine learning versus deep learning. Third, robotic process automation, or RPA. And finally, the digital workforce benefits. So, Section 1, AI and its subfields. Let's map out the landscape. You can really just think of these concepts like a set of nesting dolls. This brilliantly illustrates how they all fit together. Artificial intelligence is the largest outermost circle, right? It's the absolute broadest concept. Inside of that, we have machine learning, which is a specific subfield of AI, and nested perfectly right inside of machine learning is deep learning. So basically, every deep learning algorithm is machine learning, and all machine learning is artificial intelligence. But of course, it doesn't work the other way around. Moving on to Section 2, machine learning versus deep learning. how do these algorithms actually learn? The fundamental difference here really just comes down to how these respective algorithms learn. With classical or non-deep machine learning, you actually need quite a bit of human interaction. Human specialists literally have to manually develop the hierarchy of characteristics so the machine can comprehend the distinctions between data inputs. Because of that, it generally requires highly structured data to learn. Deep learning, on the other hand, automates a massive portion of that feature extraction step. It can ingest totally unstructured data in its raw form. We're talking things like blocks of text or raw photos, and it automatically establishes that hierarchy of characteristics to differentiate categories, all without needing a human to sit there and interpret the data for it. Because deep learning drastically reduces that need for manual human involvement, it allows us to use vastly bigger data sets. And this is exactly why Lex Fridman, in a presentation at MIT, referred to deep learning simply as scalable machine learning. By removing that human bottleneck from the data interpretation phase, we can scale these learning algorithms in some incredibly exciting and expansive ways. Now, to see exactly how deep learning achieves this, take a look at this deep neural network architecture. You see the input layer on the left and the output layer on the right. But look at all those interconnected circles in the middle. Those are multiple hidden layers. And it's within these hidden layers that the automated feature extraction process actually takes place. The network processes the raw data, passes it through these layers, and automatically discovers the patterns and characteristics it needs to make sense of the information. It's like a giant puzzle solving itself. So the absolutely crucial point here is what the word deep actually means in this context. It's not some philosophical term, it's a purely structural one. In the world of data science, deep literally just refers to a neural network that has more than 3 layers, counting the inputs and the outputs. If it has that multi-layered architecture, boom, it qualifies as a deep learning method. Now, this brings us to a really fascinating crossroads. We've just spent time looking at the brains of the operation, right? We see how algorithms can process vast amounts of data and essentially think. But thinking isn't doing. If a deep learning model figures out a pattern, who actually goes into the system, types in the data, moves the files, and executes the physical business tasks? Algorithms can think, but who actually executes the work? Which brings us to Section 3, Robotic Process Automation, or RPA, the execution arm. Robotic Process Automation, or RPA, is all about software robots, or just bots for short. These are programs developed to literally study human digital behaviors. They watch how a user interacts with a computer, and then they simulate and execute those exact same rules-based business processes. Give your bots instructions and just let them complete the task. They communicate with applications exactly like a human would. But here's the massive advantage. These bots function continuously, around the clock, with 100% accuracy and dependability. They are the ultimate tireless workforce. Just to give you an idea of their digital skill set, which frankly totally exceeds human capability in terms of speed and endurance, let's look at what they can actually do. Consider them a digital workforce that can interact with any system. They can copy and paste data, scrape information from websites, perform complex computations, access and transfer files across servers, analyze incoming emails, log securely into your proprietary programs, and connect seamlessly to APIs. Oh, and the best part? Because they adapt to any interface or workflow, you don't even have to modify your existing corporate systems or apps to start automating. The whole shebang just works on top of what you already have. Now, you might be thinking, okay, programming a bot to do all of that sounds incredibly complex, but the reality is they're remarkably simple to configure, utilize, and distribute. So the crucial point is this: if you know how to record a video on your mobile device, you can configure an RPA bot. Moving files and automating work is literally as simple as hitting a record button, performing your task, hitting stop, and using a simple drag-and-drop interface. Once configured, these bots can be scheduled, copied, altered, and shared to conduct enterprise-wide business operations. And that leads perfectly into our final section, Section 4, the digital workforce benefits. Let's look at the real-world impact. When an organization deploys this digital workforce, they immediately see 7 distinct benefits. First up, higher productivity and higher accuracy. Bots don't need sleep, and they definitely don't make typos. That naturally leads to the third benefit, a massive saving of cost.
Fourth is integration across platforms, because, as we mentioned, bots work on top of existing applications just like we do. Fifth, all of this efficiency results in a better customer experience, since requests are handled pretty much instantly. Sixth, it provides a perfect execution vehicle for harnessing AI, taking those incredible insights from deep learning and putting them into automated action. And finally, scalability. If you suddenly need 10 times the output tomorrow, you just deploy more bots.
So we've seen how deep learning scales our ability to analyze unstructured data and how RPA completely automates the tedious, repetitive execution of business tasks, combining the brains and the brawn. This leaves us with a truly exciting proposition. Think about it. If a 100% accurate 24/7 digital workforce is handling all the rules-based, repetitive work, what incredibly complex, creative, and uniquely human problems will you and your team be free to solve next?
We're diving into a genuinely transformative and frankly fascinating approach to computing that is completely reshaping our world. We're talking about machine learning. If you've ever stopped and wondered how modern systems seem to magically anticipate your needs or recognize complex patterns way faster than a human ever could, well, you're in exactly the right place. We're going to unpack exactly how this technology works, relying purely on the data to guide us.
Okay, let's dive into this with a pretty massive paradox. For decades, we basically thought of computers as these rigid machines that could only do exactly what we explicitly instructed them to do, literally step by step. But today, we have systems doing things they were never explicitly programmed to accomplish. No human wrote the rules for it, so how is that even possible? How does a computer learn to solve a problem it hasn't been given the specific instructions for? That's the exact magic we're unpacking today.
So, here is our roadmap for the explainer today. First, what actually is machine learning? Second, the logic of learning. Third, traditional versus machine learning. Fourth, the 5 ML approaches. And finally, we'll wrap up with a focus on supervised learning.
Section 1. What is machine learning?
And this brilliantly illustrates how it all fits together. Think of it kind of like a set of nesting dolls. Artificial intelligence is the big, overarching field. Inside that broad category sits machine learning. And nested even deeper inside of that is deep learning. So whenever we talk about machine learning today, just keep in mind we're talking about a very specific, incredibly powerful component of the broader AI landscape.
According to the research, at its core, machine learning is a branch of study devoted to systems that literally learn. It uses data to improve its performance on a given set of tasks. So instead of a human programmer sitting there hard-coding a rigid solution, these machine learning algorithms construct a mathematical model based on training data and sample data. By chewing through all that information, the system generates predictions or conclusions completely independently. But how does a machine actually learn from a bunch of data?
Section 2, the logic of learning.
Well, think about how we humans figure things out. The entire premise underlying these predictive learning algorithms is that tactics and conclusions that worked well in the past are highly likely to keep working well in the future. It's basically historical repetition. Take this super clear, relatable deduction. Because the sun has risen every morning for the past 10,000 days, it will likely rise again tomorrow. We learn from what's happened before. Machine learning operates on this exact same foundational logic. It uses historical data to forecast future events.
Now, what's really interesting about this is that ML goes way beyond just simple repetition. It can handle incredible nuance. For example, it can look at a giant puzzle of complex relationships, like noting that a certain percentage of geographically distinct animal families have color variations. And from that, it can deduce a specific, highly mathematical probability that an unknown black swan exists out there somewhere. It takes that basic logic of past experience and scales it up to juggle highly complex variables.
Section 3. Traditional versus machine learning. So you might be wondering, if we have regular software, why even use this? Well, the source material draws a very clear line here. For basic jobs, it's totally feasible for a programmer to manually build an algorithm that explicitly tells the machine every single step needed, no learning required. But for complex jobs, it becomes impossibly difficult for a person to write out all those steps. There are just too many variables. Actually, scratch that, it's more like an infinite number of variables. In reality, it becomes way more efficient to just assist the computer in developing its own algorithm rather than trying to handhold it through every single step.
And this is where things get real. Think about massive, messy, real-world applications, like diagnosing in medicine, filtering thousands of spam emails, parsing human speech, or giving computers the ability to see and process visual images.
For stuff like this, traditional algorithms are absolutely impractical. The data sets are just too vast and unstructured. Machine learning techniques aren't just a nice-to-have here. They are a fundamental necessity to get the job done. And because there's no single perfect solution for all these crazy complex problems, researchers have developed a few different ways to teach these computers.
Section 4. The 5 ML approaches.
So, machine learning systems generally fall into one of 5 major categories, and it's all based on the type of signal or feedback the system gets. You have supervised learning, which uses labeled data; unsupervised learning, which finds hidden structures on its own; semi-supervised, which kind of blends the two; reinforcement learning, which operates on a reward system; and dimensionality reduction, which simplifies massive, overwhelming sets of features.
Let's move to Section 5 and see how this builds into our focus on supervised learning.
We're going to zero in on supervised learning because it gives us a great concrete example of how this all works. In supervised learning, the algorithms construct a mathematical model from a dataset that includes both the inputs and the expected outcomes. This collection of examples is what we call training data. Each example is represented by an array or vector, often called a feature vector, and the whole set of data is represented as a matrix. Because the data includes the expected outcome, we basically give it an answer key, which is known as a supervisory signal. This even includes cool subfields like similarity learning, where the system uses a math function to figure out how closely related two items are, which is exactly what powers everyday stuff like search rankings, recommendation systems, and face verification. Now, within this supervised approach, the algorithm usually takes one of two main paths, depending on the kind of output you want. If your outputs are limited to a specific set of values, we use what's called classification algorithms. A perfect example is a spam filter. It takes an incoming email and categorizes it into a specific folder, like inbox or spam. On the flip side, if the outputs can take on literally any value within a given continuous range, we use regression techniques. But the key takeaway here is that both methods rely entirely on that initial labeled training data to get started.
So the absolutely crucial point is this. The ultimate goal of supervised learning is to iteratively optimize an objective function. Basically, the algorithm is trying over and over to discover a mathematical function that works so perfectly that when you finally give it brand new, unlabeled inputs, data it has literally never seen before, it can still accurately predict the proper output. When an algorithm consistently improves its predictions on fresh data over time, that is when we can officially claim the machine has learned.
Which leaves us with a truly fascinating question to ponder as we wrap up today. What happens to our world, our businesses, and our daily lives when algorithms continue to learn to optimize their own objective functions? When they unlock solutions and recognize patterns that human programmers could never, ever hard-code themselves? We are standing at the edge of an era where machines don't just calculate anymore, they learn. Thank you so much for joining me on this deep dive through the data